很多车来，嗯，嗯， Okay. Split not work for the rest. Send an email about the exam time. A quiz for next week. Hopefully our lecture will be done by next week, and then the last week we will do some revision and maybe go through tutorial question if you exercise so that we can do together. Alright, let's start the lectures today. Hopefully today is the last lecture for graph. So let's recall what we did a few weeks ago. So for the past 3 weeks, we're for graph. Okay, so graph consists of two data. One is vertex set, one is H. Okay, and then we try to color the graph and then look at locally how the graph look like. Then we enter the subject called trees. Okay. So in trees, we don't want simple circuit. So we'll remove some vertex to make it a tree. And then we randomly pick one one vertex. Then we can, for example, let's pick this as a root. So then we will form a okay, such that all the other vertex are directed away from the and then we introduce some terminology like parents, ancestor, descendant, child, leaves, internal vertexes. Okay, so leaves are those without children, and then the internal vertexes are those with children. Okay, so this was what we did last week. So before we introduce a few algorithms, we will keep looking at new terminology first. Okay, before that, application for trees. If you replace your vertexes with chemical atom, for example, carbon and hydrogen, then you can use tree to draw your chemical substances. Okay, example of tree: butane and isobutane. Or you can use for your organization chart or family tree. Organization chart start from president, vice president, and then secretary, treasurer, committee member, and so on. Okay. And next one is for your computer file system, where the root is the root directory, internal vertexes are the directories, and these are the file. Okay. So when you look at the file, you got a lot of name, right? Slash, slash, slash. So all those are directories. And then until the end, you got the file. And you can draw the tree out. You check to find where's your file. Okay, so this is the example of trees. Next, we care about rooted trees. Got how many children? If the rooted tree have no, or if for all the internal vertex has no more than m children, we will call it a emery tree. Okay. If all of them have exactly m children, we call it a full emery tree. When m equal to 2, we call it a binary tree. So let me draw you the binary tree picture. So a binary tree, you have when m equals to 2, you have all the internal vertexes have no more than 2 child. Okay, so this is a binary tree. But it is not a full binary tree, okay? Because you only have one child here. Okay, this one is a binary tree, but not full. Okay, so to be full, all the internal vertex must have 2 child. Okay? So this is the difference between binary and full binary. Okay. Okay. And next, later we will form some theorem using a full binary tree. We can have some control on the leaf, the number of leaf and number of vertexes. Okay. Next is the ordered rooted tree. Okay. So what is ordered? So the children are ordered. Children are ordered from left to right. Okay. So in the binary tree, we'll call the left one the left child. Okay. And then the right one the right child. And then if there's a subtree having the left child as a root, we will call it a left subtree. Okay. If there's a subtree having right child have a root, we will call the right subtree. Okay. Okay. So left child, left subtree, and right subtree. Okay, next. A tree with n vertexes has n minus 1 edges. Okay. So this is a theorem. So you can prove it by induction. So when n equals to 1, okay, the tree is supposed to have how many edges? 0. Can you have 1 edges? Why not? So if you have 1 edge, you have to have the loop, which is a simple circuit. Okay, so you cannot have this case. So you need to have 1 vertex. How about 2 vertex? How many edges can you have? Huh? Sorry, 2 vertex, huh? Oh, I mean, okay, yeah. One to connect them because 3 need to be connected. Okay. If more than 1, then you will have loops or simple circuit or not a simple graph. Okay. And then you can show it by induction that you always have n minus 1 edges. Okay. Okay, next. If you want to look at the proof, you can, I think, textbook on it. Next is a full emery tree with I internal vertexes contain m times 1, m times I plus 1 vertexes. Okay, so what's I? Why I is the internal vertex. So how to understand this theorem here? So full emery tree meaning all the internal vertex have m children. Okay. So all of them have m children. And the question is, how many vertexes do you have in total? Okay. So every internal vertex have m should I Okay, let me use product rule. Okay, maybe I use product rule to describe. Okay, so internal, yeah, sorry, the graph, the, yeah, actually, I just mean this. Okay, okay, so let's maybe, okay, so we got V1, V2 up to VI, okay, and then maybe children, we put C. So, okay, maybe let me draw it. So every internal vertex you have C1 up to the, maybe draw like this, C1 up to CM children, okay? So in total you have M times I Y plus 1 because this one comes from the root, okay? So M times I only add up for the bottom one, okay? But not the top one. Can see it? Can see it? Can, for example, I label here C1, V1, C1, and V1, CM here because this guy is V1, okay? Okay? And then this one maybe V2, okay? So plus 1 here is because of the root. Okay. Okay, next, like last time what we said, the internal vertex and the leaf partition the vertex set. Okay. So the number of vertex is equal to the number of internal vertex plus the number of leaf. Okay, this is what we said last time. So from here we can build a theorem. So a full memory tree with n vertex. Okay. We only need to know about how many uh, children that every internal vertex exactly have and the total number of vertex, then we can figure out the number of internal vertex and leaf. Okay, so you at first it might look a bit daunting, but if you move it around, it's just the formula we get just now. Okay, n is equal to im plus 1, right? Just now we have this formula here. And then the how to get this one. So this one is just combine what we said just now. N equals to I plus M. Okay. And then to find L, you just take N minus I. And I is this fraction here. Okay. So N minus this fraction here, you get this after some factorization. Okay. You agree? I need to show you, or you happy with it? Are you happy with it? Okay. Yeah. So you just take N minus the I. Okay. And similarly, if I just tell you the exactly how many child the for every internal vertex and internal the number of internal vertex, then you can compute the vertex and leaf. Okay, so you can see that you just use the same formula. Okay, use the same formula. Okay, so uh so of these three, hello, long time no see. Okay, uh So the proof of these three theorem here is just keep repeating using this two formula here. N equals to in plus R1 and then n equals to I plus L. So this one connects n with the internal vertex and the uh, what's n? The children, the number of children, and then n connects internal vertex and leaf. Yeah. So these two equations determine these numbers. Okay. So maybe you think that this one is a bit boring because just calculate the number of internal vertex and leaf. Okay. So actually, your textbook I think give out quite a good example here. So the examples read like this. Suppose that someone starts a chain letter. Each person who receives the letter is asked to send it on to 4 other people. Okay. Some people do this, but others do not send the letters. Okay. How many people have seen? The question is, how many people have seen the letter, including the first person? So the first person is the root. But if no one received more than one letter, so this means there's no circuit here. Okay, so you can form a tree. There's no circuit here because no one received more than one letter. And if the chain letter ends after there have been 100 people who read it but did not send it out, how many people send out the letter? Okay, so let's see if we translate this to a tree language, what we get. Okay, so whoever receive it is asked to send on to 4 people. Okay, so some do this, but some didn't. So that means either you read it, you send it to 4 people, or you read it, but you didn't send it out. Okay, so either 1 to 4 or 1 to 0. Okay, so what tree you can form? You can form one uh, quaternary. I think it's quaternary if a proper word. Quaternary trees. Okay, right. So either you send to 4 or you don't. Okay. So in this case, what are you asked to find? You're asked to find how many people seen the letter and then how many send it out. Okay. So in this language here, so root is the first person, first person. And then what's the leaves? Okay, leaf have no child, right? Okay. So leaf are the person that read, but no, then okay. And then internal vertex, people who read and send. Okay. Okay. Yeah. Okay. So this means all the vertex are the guy who read it. Right. So all together, so if you combine the two number are the people who read it. Okay. So you are told that 100 people who read it but did not send it out. Okay. So this one is what kind of people? What kind of people is this? No, this kind of is irresponsible people. Just kidding. Okay. So these people are leave. Okay. So 100 people are leave. Okay. And then how many people who have seen the okay? So you are asked to find uh n. So you got yeah. Don't use M. Later you confuse it. Use P and Q. Okay. So you have 4, you have 100, then you can figure out the other two numbers. Okay, using the theorem. Two numbers can figure out the other two numbers. Okay. And got it? Got it? Okay. Can use the formula. Yeah. Yeah. Okay, next. Next, we'll talk about the level of the vertex. Level of the vertex. So starting from trees, the root will be at level 0. Okay. And then the level of the vertex will be defined to be the length of the path from the root to the vertex. Okay. So if your vertex have length n path to the root, then uh, the level is level n. Okay. So for example, this the child of the root, this child, the left child have length 1 path to the root, so it is in the level 1. Okay, and then you can go on. Okay. But the key here is we set the level of the root to be 0. Okay. So that the length of path makes sense. The definition of length of path. And then the height of the rooted tree is the maximum level of the vertex. Okay. So for example, the height of this example here is 3. Okay. So it's the maximum level. So in other words, the height of a rooted tree is the length of the longest path from the root to any vertex. Okay. So you can find the longest path here is to the root is actually length of 3. Okay. It's the same. So this one is level height. Okay. Then we'll talk about how a rooted tree of a height h is balanced. Okay. So it is balanced if the tree is balanced if all the leaves are at level h or h minus 1. Yeah. So all the tree must be only at the maximum height or maximum height minus 1. Okay. If there are leaves at maximum height minus 2 or less, then it will be imbalanced. Okay. So you can imagine that maybe this tree can fall down. So it must be at the h or h minus 1. Only these two levels is allowed. Otherwise, it will be imbalanced. Okay. Okay, next is a tree traversal. Okay. So tree traversal, what do? Is we want to traverse all the vertex. We want to find an algorithm to go through all the vertex systematically without missing anyone. Okay. So first kind of algorithm we did is called the universal address system. Okay. So what we do in this universal address system, we label the root as 0. Okay. And then we label the child of the root as 1, 2, 3, 4, 5, and so on, starting from left to right. And then for the next child, for example, the child of 1, we'll put 1.1, 1.2, 1.3, 1.4, and then 1.6. How about the child of 1.1? We will put 1.1.1 and then 1.1.2, and then keep going. So we keep the previous label and then 0.1. Make sense? Make sense? Okay. So, but how we go through the order? So we will put 0 first. Okay, 0 first, and then 1 is greater than 0, and then 1.1 is greater than 0, and then if you have 1.1.1 is greater than 1.1, and then only then you keep going to the left. So for example, in this case, in this example here, 0 is less than 1, 1.1, less than 1.2, less than 1.3, and then less than 2, and then less than 3, and then less than 3.1, less than 3.1.1, and then less than 3.1.12, and then less than 3.1.2.1, and then going up to 3.1.2.4, and then less than 3.1.3, and then less than 3.2, and then less than 4, and then like this. Okay? Makes sense? Okay. 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 So, yeah. So the procedure of systematically visiting every vertex of an ordered route are called the traversal algorithms. Okay. So these are the traversal algorithms. Okay, next we will introduce another three traversal algorithm. So first is called the pre-order traversal. Okay, later we'll see why it is called pre-order. So let's say you are given an ordered rooted tree with root R. Okay, if the tree is just one vertex, okay, then the vertex is the pre-order traversal of T. But let's say your tree got T1 up to Tn subtrees, okay, labeled from left to right. Okay. Then the pre-order traversal begins by visit R first, okay, and then continues to traverse T1, the left subroute, and then T2 up to Tn, the right subtree, okay. So what does this mean? So for example, this example here, okay, let's look at the example here. So we make this definition, we summarize this definition using this three step here. So first, visit the root. Second, traverse the left subroot subtree. Actually, the more accurate one should be leftmost subtree. Okay, only leftmost, and then traverse all the right one. But we just said visit the root, leftmost and then right. Okay, so 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 for example, in this case here, you visit the root first, okay, and then you need to break your subtree into the leftmost and all the right one. Okay, so this one is the left, the right. Okay, so you start with visiting the root, transverse the left subtree. Okay, when you transverse the left subtree, this is not a vertex yet, so you need to repeat this algorithm. So you need to visit the root and then transverse the leftmost subtree and then transverse the right subtree. Okay, only when it becomes a vertex you can write down your order. Okay, so let's do it again. So so you are given this ordered tree, right? So this is important. This will be come out in the end. So if you're given this tree here, okay, so what you do is you visit the root first. Okay. So visit the root is already 1 point, so you can put down the vertex. Next, you need to transverse the leftmost subtree. Okay. But when you transverse the leftmost subtree, it's still a tree. So you need to go through this process. So you need to visit the root, transverse the leftmost subtree, and transverse the right subtree. So what you get is visit the root, transverse the leftmost subtree, and then transverse the right subtree. And then you continue the previous algorithm. Because you finish transverse the leftmost subtree, you need to transverse the right subtree. So you can see. Okay. So this is the pre-ordered transversal. Okay. So from these three pattern here, right, we can permute these three patterns. Okay. So we can either visit the root, transverse the leftmost, and transverse the right one, or we can transverse the leftmost first, and then visit the root, and then transverse the right subtree. Or we can do 2 and 3 first, and then visit the root last. Okay, and then this result in 3 different order transversal. So first one we call the pre-order transversal, which is what we go through just now. And then second one we call the in-order transversal. And then the third one we will call it a post-order transversal. Okay, so you can see that why pre, why in, why post. This one is actually this one reflects when you visit the order, visit the root. Okay, so pre-order you need to visit the root first. In order you visit the root in the middle step. Okay, 2, 1, 3, and then post order you visit the root last. Okay, make sense? Okay, but this one is just summarize of the definition. If you want to see a precise definition, you should go to the textbook, and I'll attach the definition in my lecture note as well. Okay, so maybe let's go through one more example for the pre-order transversal. Okay, so this tree is a bit larger. So let's try to do pre-order transversal on this ordered tree. Okay, so remember what's the step for pre-order transversal? Visit the root first. Okay, transverse the leftmost subtree. Leftmost subtree. And then 3, what you do? Transverse, not rightmost, all the right one. You need to transverse all the right one. Okay, right subtree. Leftmost mean only one, the most to the left one. Yeah. Okay. Okay. So first you need to visit the root first. Okay, and then transverse the leftmost subtree. Okay, only then you transverse the right subtree. But to transverse the leftmost subtree, okay, this is still a tree, so you need to repeat the algorithm. You need to visit the root first, transverse the leftmost subtree, and then transverse the right subtree. Okay, but here is still a tree, so you need to visit the root first, transverse the left subtree, and then transverse the right subtree. And then this subtree is a tree again, so you need to transverse the left, visit the root, transverse the leftmost subtree, and then transverse the right subtree. Yeah. So let's see what we get. So first, you visit the root. Okay. A. Second, you transverse the leftmost subtree. Okay. So to traverse the leftmost subtree, you first visit the root first, okay? And then you transverse the leftmost subtree. But when you transverse the leftmost subtree, you visit the root first. And then you transverse the leftmost subtree. So you get J. And then after you finish transverse the leftmost subtree, you need to transverse the right subtree. Okay? When you transverse the right subtree, you start with visiting the root. And then after you visiting the root, you transverse the leftmost subtree. Okay. And then you transverse the right subtree. Okay. O and P. Right. Okay. After you transverse this leftmost subtree, you need to transverse the right subtree. Okay. And then you transverse the whole leftmost subtree on B. Then you need to transverse the right subtree. Okay. C. And then what you keep doing, you transverse the leftmost right subtree. So you need to visit the root and then transverse the leftmost subtree. So when you visit transverse the leftmost subtree, you need to visit the root again, and then transverse the leftmost subtree, and then transverse the right subtree, and then transverse right subtree. Okay? Yeah, I missed out anyone. Let's check. Okay, yeah, correct. Okay. Any question on this use executing this algorithm? Any question? No? Do you want to do in order or post order? Is okay. How about the others? You want to try in order or post order, or you can try yourself. Or in order. Okay, try in order. Okay, so let's try in order. Okay, so we have the same tree, I think. Yes, correct. We have the same tree, but now we play around with the procedure a bit. So first we traverse the leftmost subtree. And second, we visit the root. And then third, we traverse the right subtree. Okay, so now it's a bit different already. Yeah? So we don't visit root anymore. Okay. So first we transverse with the leftmost subtree. Okay. Only then we visit the root. Okay. So we need to transverse this leftmost subtree first. So to transverse this leftmost subtree, still a tree, so we need to go through this algorithm. So I need to transverse the leftmost subtree and then visit the root. Okay. But to transverse this leftmost subtree, we need to transverse the leftmost subtree. Okay. So we start with J. Okay. After we transverse this leftmost subtree, we need to visit the root. Okay. So we visit root, go E. After going E, we transverse the right subtrees. Okay. So to transverse this right subtree, we need to repeat this because it's a subtree, it's a tree. So we transverse the leftmost subtree first. And we get N. And then visit the root. Okay. And then transverse the right subtree. So we got O and P. So after we transverse the right subtree, what we do? We transverse the leftmost subtree. Transverse the right subtree. Okay, we done already. We visit root already. We transverse the. Okay, then we need to go back to this transversing this leftmost subtree, right? So after we transverse this leftmost subtree, we need to visit the root. So visit the root, and then we transverse the right subtree. And it's F. So after we transverse this leftmost subtree, we need to visit the root. So after we visit the root, we transverse the right, and then we transverse the right subtree. So to transverse the right subtree, because this is a tree, right? So we need to go through this algorithm again. So we need to transverse the leftmost subtree. And to transverse this leftmost subtree, we need to transverse the leftmost, leftmost subtree. So it's L, A, and then what we do? L, after L, we need to visit the root and then transverse the right subtree and then visit the root, right? Because we finished this tree already. So we need to visit the root, and then transverse the right subtree. Okay, I think done. Let's check. Yeah. Okay. Yeah. So this one is in order. So we also go through all the vertex, but in a different order. Huh? Oh, what? What do you mean stop and see? Go back to tree. See? Oh, which step, huh? So actually, this step haven't finished. This step means you need to keep traversing the right subtree. Okay. So it's yeah. Okay. So if you go and read the definition, right, you can see here. Suppose T1, T up to Tn are this one is post order. Okay, let's read the in order. So suppose T1 to Tn are the subtree at R. The in order transversal begins by transverse T1 in order, then visit the root. Okay. And then it continues by traversing all the rest. Okay. So T1 visit the root. So that's why I put a leftmost. So only the first one come first, and then go to the root, and then go do the rest. Okay, let's take any more question? Any more question? Others? Got question? Maybe take a breakfast 9:55. You want to take breakfast also can. 9:55 we come back. Ah, 根本人不见一般进去。
所以现在是在讲哦，打到从左边的开始，然后打到 root，接下来就是一直往右边。
Yeah.
OK，
对。哎，你要学会读哦，你不会只听我解释吧？你要听我解释啊，然后你去读，不然
从早读课本，
你以后等下永远读不懂
好像听得懂，
啊！是啊，
以前听不懂哦，
是啊，
痛苦哦，听你讲你听不懂，看你看不懂。
对啊，慢慢进步，慢慢进步。
现在你给我看这个，我好像看得懂，
你现在看得懂啊？
好像看得懂啊，
对啊，如果我没有解释给你，看得懂吗？
应该可以。因为昨天不是拜二我不是也去上
啊
那个是我 Emery 啊，比较迟来一点，然后我看那个课本
，OK，
就很容易理解吧。
反正这一次，什么？这一次哦，讲的，什么东西很难？什么东西很难？什么东西很难？什么东西很难？你不是讲容易啊，然后又讲难啊？
这种考试看不懂。
这个没有很多啊，但是有。
OK，简单。
那你会拿，
OK，
不要弄乱就是了。
OK，简单。你真的那个是一点点
我跟你讲，不要用脑想的东西都是简单的。
用电脑这个对不对啊？这个要细心哦。
呀，要细心啊，不要粗心啊。这个不用脑也可以做，是不是？
然后用脑，连笔都不能脑。
去哪里买啊？去哪里买？哪一间？哦，B1，你们可以去到 B1，其他同学不进去啊，同学不进去，看球赛啊。 Okay. All look so tired. Watch FIFA. Uh, but too many assignments. Too many assignments. What you guys do? Why so tired?
So many quiz.
So many quiz? What course no quiz?
Assignment.
Assignment.哎，
放着羊了没？
OK，还好吧？对
还有点。
对。
这个不是说是穆斯特莫 F
Let's move.
left the subset，为什么从这底下开始？
因为第一步你要 transverse the leftmost subtree 先。
那什么不是那不应该是这里吧？这个不是
没有没有
root 吗？然后
对
那这不就是 leftmost 的 subset？
，tree 要整棵树，
它不去。
对，整棵树，整棵树，对，这整棵树 subtree 你慢来，刚才
嗯
subtree，如果我们说 subtree root as b 的话，是所有的 descendant，对吗？比如说你倒一个水进来，这里全部都会动到，如果跟着这个线跑的话，所以这个叫做 subtree at b，对吗？
嗯
对，所以如果我讲 transverse 的 leftmost subtree，就是这整棵树你都要看，可以吗？
嗯。
但是你要看这棵树的时候，它是一棵树，所以你要重新跑过这个 algorithm 算法，
哦，然后又跑到底下。
所以就跑到底下，然后再跟着这个咯，理性的就跟这个咯，但是到这里就停了嘛，因为如果是一个点，我们就取那个点。OK，
那这个也算是 subtree，
对
是
，right，
K 的 subtree，
就是 K subtree，对，没错，没错，没错。
然后要从最小的那个去。
对，如果你要看这个 tree，然后你再重复这个步骤，看这个 leftmost subtree，and then visit the root，and then transverse the left
是去到小的去一起。
好的，这样写完，都是这样，都是这样，
所以这个是这个大的去的 most
对，subtree，
subtree
对
leftmost subtree。
对，
subtree 只是先访问这个，是因为是整个
对，
大的
没错，
leftmost subtree。
没错，没错，
然后这个也算是它的 subtree，
没有错
这个点也是。
，yes，因为它这个变成 root 了嘛，对不对？
嗯。
每个树肯定有 root 的嘛，所以这个是 root 哦，
哦，然后这个又变成
变成它的
subtree，
对，没有错，
访问 root，
是
然后访问这个
right subtree，
red subtree，然后 red subtree 里面这个就是 root，这个就是
没有错
left
，OK，
subtree。
yeah，
哦。
yeah，没有错。 嗯，啊，想做什么？你也伤害。哦，有没有？哦，因为我觉得这个东西写了啊，越写越乱了。对啊，也可以抓了。然后因为每一堂课都有人在问东西的。这很快啊，很快。我就觉得快。对对对，那时候又有一些状况，那时候又有一些状况，然后啊，对对对对对，因为感觉他们听漏了什么东西嘛，就那时候我是听不懂，还是不知道。对，我是说现在更听得懂。哦，对，可以跟那个梁小来。哎，那个梁小，哎，那梁小小梁，在后面的。我昨天讲太快，我是要讲快一点，看他们第二年嘛，然后现在讲更快，好像有点超速。昨天有些听得懂啊，感觉好像有些听不懂，有点超速了。啊，Okay, do you want me to go through the post order example? 节目表哈，boleh juga, boleh ya? Okay ya. So let's go through quickly. So post order, first step, what you do? Transverse the leftmost subtree. Second step, what you do? The right subtree. Right subtree. And then last, what you do? Visit the root. Okay, you visit the root last. Okay, so maybe let's go through this a bit quicker. So transverse the left subtree. So you need to transverse the left subtree first. Okay. And then to transverse this left subtree, you need to transverse the left subtree again. To transverse this tree, you need to transverse the leftmost subtree. So you start with J again. So after you transverse the leftmost subtree, you need to transverse the right subtree. But to transverse the right subtree, you need to transverse the leftmost subtree. There you go in. And then transverse the right subtree. Only then you go back to visit your root. And then after you traverse the left most subtree and the right subtree, you need to go back to your root. And then after you traverse the leftmost subtree, you need to traverse the right subtree. And then you visit the root. And then you traverse the leftmost subtree. Can still following? I didn't draw, see if you can follow or not. Okay, so finish the left, go to the right. Go to the right and then keep going to the right. Okay, so this right tree is still a tree, so you need to traverse the leftmost subtree, and then to traverse this leftmost subtree, you need to traverse the leftmost subtree. So you need to go to L. Okay, let me don't say, see you can do it correctly or not. What's the L after L? And then G, H. Yes, yes, yes. See, let's check. Yesterday answer still there. Yes. Okay, good. Okay. Okay. So in textbook, there's one way using this path here. Okay. Different way of reading this path here can give you all three different order transversal. But I won't discuss it. You can go and read it. If you do many example enough, then you will easily understand what they say. Okay. Hello, Dan So Shen. Okay. Next. Okay, next. Okay, next is what we call a spanning tree. Okay. So to understand the spanning tree, you can think of a backbone. Okay. Backbone of a animals or human. Okay. So for example, if you start with a simple graph, okay, you start with a simple graph. Start with a simple graph. What else you can do? Okay. You start with a single graph. A spanning tree is a subgraph of the graph that is a tree and contain every vertex of G. Okay. So for example, one spanning tree I can get is something like this. Okay. So it's a tree. There's no simple circuit. So you should think of the backbone of your spanning tree. And then come out from this. So there are different spanning tree you can pick, right? For example, you can pick this. You also can pick this. Okay. This and then this. Okay. These are two spanning tree. Okay. As long as you contain all the vertex and then they are connected, no simple circuit. Okay. No simple circuit. A simple graph is connected if and only if it has a spanning tree. Okay, so this should be obvious from the definition. Because if the graph is connected, then you can uh, construct a spanning tree. Okay, because it's connected. So every two vertex is connected by a path. So you can construct a spanning tree. And if you have a spanning tree, the simple graph should be connected because in spanning tree, all vertexes are connected. Maybe one way is trickier, but not too difficult, this theorem. Okay, so there's an algorithm to find the spanning trees. Okay, there are two algorithms. One is called the depth first search. Okay, you will see why is it called depth first search later. So what you do is first you just start with any point, start with any vertex. Okay, choose one vertex as your root. Second, what you do is you form a path by adding the vertex and edge as long as possible. Okay. And If it is not a spanning tree yet, you should return to the last vertex, which is adjacent to the vertex that is not yet visited. And then repeat 2 and 3 until a spanning tree is obtained. Okay. So remember just now we say a spanning tree of n vertex must have how many edges? N minus 1, okay? So that's mean you need to stop at n minus 1 edge. Okay, let's see how we implement this algorithm here. So look at this graph here. So let's say, for example, we start at F. Okay, we start at F. Start at F, and then we can keep forming edge and vertex, okay, as long as possible. So what we do is we start at F, go to G, go to H, go to K, go to J, and then start here. Okay. Have you found a spanning tree yet? No, right? Because you still haven't reached all these number, all these vertex. Okay. So you need to go back to the last vertex, which is adjacent to a vertex that hasn't been visited yet. Okay. So you need to go back to H and then go to J again. Okay. And then this side all done. So you need to go all the way back to F. Okay. And then what he do is he go to D, go to E, go to C, go to A. Okay. But you haven't visited B yet. So you need to go to the last vertex that is adjacent to B. So you go to B. Okay. Make sense? Make sense? Okay. Let's try one example. Okay. Try one example. So which vertex you want to start? Let's try one example together. Which vertex? J. Okay, J. Sure. Okay, J. So J, where you can go? You can go to K. Okay. And then you can go to H. And you can go to G. You can go to F. You can go to E. You can go to E. Go to E. Go to A. But you haven't reached B yet, right? So you need to go back to the last vertex that is adjacent to B, which is C. So you need to go to B. Who else haven't reached yet? H, I, huh? Okay, so we need to go all the way back to H, then go to I. Okay, so this one is very long. What's the height of this? 1, 2, 8, 1, 2. Yeah, height is 7. 8. Okay. Okay. What's the height of this? 4, 1, 2, 3, 4. Yes, height is 4. Okay. Yeah. So that first search will result in a very tall tree. Yeah. By the way, tall is the word I invent here. Okay. Okay. Next is called the breadth first search. Okay. Not breakfast, breadth first. So breadth is the wide. How wide is it? Breadth. Yeah. Just now it's deep. Depth. How deep? It's not how wide. Breadth first. Breadth first. Okay. So what you do is also you pick a random route. Okay. Random vertex. And then the second step is different. You add all the edges incident to this vertex first. Okay. So every vertex that's adjacent to it, you add all of them. And then you repeat this step for all the children until you obtain your spanning tree. Okay, let's see this example here. So we start with a G, okay? And then let's say we start with E. Okay, E is the root. So everyone that's connected to E, you add it first. Okay, for example, D, B, I, F. Okay, you add all of them. Next, you add everyone that's connected to B. So who is connected to B? A and C. So you add A and C in. How about D? Who is connected to D? A and H. Okay. But you can see that B is already connected to A. Can I connect D to A again? Why not? Huh? So you will, if you connect D to A again, you will form a circuit. Okay. So in the tree, we don't want circuit. Okay. So since B already connected to A, D just need to connect to H. Okay. And then you do it for the rest. And then you keep doing it. Okay. Uh, you want to see one more example on this one? Or not? If you want, you can shout out one vertex. K, yeah. Where's K? Oh, I found K. Okay. So let's start with K. Let's say we start with K. So to use this algorithm, we need to choose a random vertex and then add all the adjacent vertex. So who are adjacent to K? They are M and I. So no one connect to M, so M can stop already. How about H? H is connected to I and D. Okay. So can I connect like this? Why? Okay, so you're from the circuit. So in the algorithm, you should say you need to avoid circuit. Okay. So H is connected to D. I is connected to who? E and F, B, and F. Right. Can see it? E. Sorry. Sorry. Did I see the wrong thing? Yeah, I is connected to E and J. Sorry. E and J. Okay. Correct. Correct. Okay. How about D? D connects to who? D connects to A, connect to E. Okay, but E already in there. How about E? E connect to B, and then E connect to F. Okay. How about J? J connect to F. J connect to E. J connect to C. J connect to G. Okay. A connect to B. B done. B connect to C. C done. F connect to J. J done. G done. Huh? J to C. J to C is wrong. So what happened here? J to who? J to F, J to G. Okay. So maybe we need to get B to C here. Okay, good. And then F to G, G to L. Okay, I think that's all. Is that all? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, 10, 11, 12, 13. Okay, done. Okay. So this is the spanning tree. How about we compare these two methods here? Okay. How about let us start with F. Same. We start with F, and then we use a different algorithm, see what tree we get. Okay. So we start with F. Okay. So F, who are connected to F? D, E, G, and H. Okay, good. So who are connected to E? Yeah, I believe you. I don't want to check. C, and then who else? No more. Only one. How about E? Yeah, 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 yeah. E to C, huh? Okay. D, nothing. E, nothing. Okay. And so E to C, and then what else? C to A, B. Okay. E, E nothing. H I N. Okay, and then there. So what's the height of this? 1, 2, 3. Good. So the height is 3. And you can see that you can compare these two trees here. You see, this breadth, you see, got 4 children for the root, but here only got 2 children. Okay. So it's in general, breadth first, it's wider the tree. Okay. Wider is I invent one. There's no this kind of word. Don't try exam. I invent one. So this one is wider. And then you can see that this that first tree is generally taller. Okay. The height is greater. Okay. Okay. Yeah, that's all for these two. And then you can write out the algorithm for computer. It's in the textbook. Okay, next is called the minimum spanning tree. Let's say, for example, we put number on each edge, right? Okay. So once you pick out the edge, you will collect the sum of the weight. Okay. Now we want to find the smallest weight. Okay. Remember last time we talked about the multiplicity of edge. Okay. We can put number on the edge. Okay. So this is we also call it a weight. So now we want to find a spanning tree that has smallest possible sum of weight. Okay. Get the idea now. Get the idea? Like we have produced different spanning tree, right? Let's say we have different weight on the edges. We want to find the smallest possible sum. Okay. So the algorithm we're gonna introduce are called the greedy algorithms. Okay. So why are they greedy? So they are greedy because they make optimal choice at every step. Okay. So you are very greedy. You want to earn the most every bit, right? But it turns out that it is still optimal for the overall process. Okay? Because in general, it is not true that if you make an optimal choice, you get an optimal choice in the end. Okay? This is not true. Okay? But in this case, these two algorithms can produce the optimal final answer. Okay? So next. So first is what we call the primes algorithm. Okay? So primes algorithm says that when you start with an edge with a smallest weight, okay, and then you can successively add to the 3 edges of minimum weight that are incident to a vertex that's already in the tree. And never form the simple circuit. So this one is what we go through every time. And then stop when n-1 edges has been added. Okay, so let's see what's this algorithm doing. So first, what you do is you start with edge with smallest weight. Okay, so you look at this figure 3 here. Okay, which one has the smallest weight? Huh? BF, CD, and KL. Okay, so the algorithm says start with one of them. Let's say we follow this example first. So we start with BF. Okay, after starting with BF, right? Let me draw. So after starting with BF, what you do is you need to look at all the edges that is incident to this previous pre-existing vertex, and then see which one is the smallest one. So for example, this case, AB and GF, okay? Which one is the smaller one? AB. So we want to add AB first. Okay. Next. Hey, sorry, just now, not just AB and FGL. You still have EF and BC. Okay, but in the end, AB is still the least one. So next, you got BC, FG, FJ, FE, and AE. Okay. So all the edge that is incident to the pre-existing vertex. Which one is the smallest one? Fj. So you need to add Fj. Okay. How about the next one? You need to consider Fg, Bc, Fk, Ij, Ef, and Ae. Which one you pick? You need to pick the minimum one. Huh? Fg. You want to pick Fg. You want to pick Fg, huh? Yes, all are three. Okay. So the special part of this algorithm, right, is if you have more than one choices, you make any choices, you still get the smallest one. Okay. Uh, we won't prove this. I think your textbook also didn't prove this. You should go and check. Yeah. So we won't go into that argument, but this algorithm will anyhow produce different spanning tree, but still the smallest way. Okay. So if we follow the example here, we will pick AE first. Okay. Later we can try different possibilities. Uh, so let's pick AE for now. Okay. Pick AE for now, and then next step they pick IJ. Okay. They pick IJ because if you look at EF, EI, IJ, JK, FG, BC, the smallest one is 3. Okay. And then they make a choice at IJ. And then you keep going on. Okay. So you pick FG because 1, 2, 3. All of them are 3. They put FG. Okay. And then next they pick CG. Why? Because you got 3, 2, 3, 4, 3. 4 is the lead, 2 is the least one. So you pick. Okay. Next, I think you should obviously pick 1 here. Okay. And then what else you can do? You got GH. Okay, yeah. Then do GH because everyone else is either 5, 3, 4, 3. This one cannot. Simple circuit. So pick a GH. And then pick a HL. And then pick a K. Okay. So maybe we can try our own example. Let's start with maybe start with KL. I never start with KL. So let's start with KL. Okay, maybe use this one. Okay, let's start with KL, right? Okay, I haven't finished this one yet. So when you add this up, the least weight you can get is 24. Okay. So that's mean if we start with different, use different choice, start with different smallest weight, we also have to end with 24. This is what this algorithm do. Okay, so maybe start with KL. So it's then wait. Let's start with KL. I never start with KL before. KL 1. Okay, second. So what can we do? JK. Okay, let's pick JK. How about next? Huh? FK, FJ, FJ, right? Right, because all are 3, 4, 2, 3. So 2 is the least one. You have to pick J is 2. Next, FB. FB. Okay, FB is the least one. Okay, how about next? BA. BA is the least one because 2 is the least one. Okay, BA. Okay, so BA 2. Okay, next. Huh? AE. AE because you got 3, 4, 3, 3, 4, 3. Okay, 3 can AE. In fact, if you want to pick HL also can. You want to pick FG also can. Yeah, as long as it's not simple circuit yet or IJ. Okay. What's next? IJ. Okay. Next. J. Yeah. Green. Lag. I'm not lag. My bad. iPad lag. See. iPad lag. Okay. So we have IJ. And what's next? What's next you want? Huh? BC. Okay. BC. BC is 3. Next. CD. This one is important, you see? This one, if you pick wrong, then you'll be wrong. Then you got 1, 2, 3, 3. So you have to pick 1. Okay. There's no choice here. You need to pick 1 here. Next. CG. Okay. Yeah. Here you also have no choice because 2 is the least one. Okay. Next. GH. Yes. Either one of them. Either you can pick IH or CG. Sorry. GH. So 12 vertexes, n minus 1, 11 edges. Okay, should be done by now. Okay, let's compute how many weight here. 24. 1, 2, 3, 4, 5, 6, 7, 8, 24. Okay. Okay. So these are two different. You see, you can see two different spanning tree, but the same. Wait. Okay, next. Okay, the final one. Final one. Kruskal algorithm. So you also start with the same weight, okay? But now when you add the vertex, the edge, you just need to add the minimum weight, okay? Don't care whether the vertex exists before, okay? You just add the minimum weight and until without forming the circuit and then until n minus 1 edges are added. Okay. So for example, this example here, okay? So first you add all the minimum weight first. So all the least one you add in first. Okay. So you add in all the one first. Okay. And then you add in all the 2. Okay. Add in all the 2. Anything else? No more. Okay. Then you add all the 3. Okay. But be careful when you add the 3, right? So this 3 we don't want. Okay. If we pick this, then we don't want this because it will form a circuit. Okay. And then this 3 maybe we add. And then if you pick this 3, then this 3 we don't want because it will build a circuit. So why I pick this 3 but not this 3? The answer is you can do whatever you want. Okay, because this algorithm will produce different spanning tree but the same tree, but the same weight, total weight. And then are you done yet? I think you're done. Okay, so this is a spanning tree. I think with total weight 24. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Any question? Huh? That's all. Any question? No? No? Okay. Maybe we take a break and then come back for tutorial. If we finish tutorial earlier, then maybe we can go back earlier. Okay. Yeah, 10:40, come back for tutorial.哎，
它就是不考那个 counting 和 relation。
好，第二个从那个 partial ordering 开始。
就是 graph 的 tree
没有 partial ordering，就是那个 relation 的后半部。
relation 后啊，
partial ordering，
这个
然后到 graph。啊，下周更轻松了。画吧。那你们电脑老师是也是这样子指下就好？你们电脑老师就 C 加加PPT，哎，谢谢，这样就好了。用 slide 要什么？
我演示给我。
还有演示有没有？哦，OK OK，没有 slide，有 slide 啊。拜拜啊，拜拜。See you next time。Hey, since we have more time today, right? Hey, you guys want to present tutorial question? Present. Pick one question you discuss and then like the different groups present. Join my meeting room. You can share your screen. Yeah.最后一周
四门考试，
四门考试啊？
只有一个老师发证，在
下周啊，下周至少下周，因为还有东西还没教完，那个现在教完，对啊，没教。 Uh, now, as you guys want to do something different over today. Want to do something different today? Huh?
Earlier today.
Oh,
There's
earlier
something
today.
different.
Huh?
There's something different.
What time? By one. Okay.
Every week.
Next weekend. Also.
Because too many holiday in one day.
Yeah.
Monday got how many classes?
One class. Which is like
Maybe once. I can't see. Forward. Forward.
然后我
该我们讨论。看一下，就 present 做的 tutorial，就做来解释啊。可以。想这样算。这样算呢？
当然因为
Many of you have tablet. Yes. Many of you got tablet. iPad or tablet. Hello. How many of you got tablet? Hello. Sleeping or everyone? iPad. Anything. You respond.
老师啊，如果你要捐给我们这些老师啊，你发现的，
Size 吗？
还在你算的，
算什么？
算的几个有个
没有人举手。
啊2万，哦，那2万，
不能看。
我记啊，今天要算。
Hey, your boss say when you go interview, they say you have to present. It's the boss don't want you for interview. The intern boss said you have to know how to present. If you don't want to present now, then in future you don't have job.
会写我。现在怎么样？点个人上来用你 iPad。哦。 等一下，怎么的？这个在地方在打开的时候，刚刚有今天一看到是一个在看往地方。要钻领域了，都球也很好看。一是对对。Try discuss with your friend. If you don't have a habit of working with them. Because in Australia we got like a lot of whiteboard, so all the students can work in small group. But there's no whiteboard here. In one, yeah. So in our tutorial room we got 5, 6 whiteboard. So everyone can write. Count that to your book.
Huh?
Count that to your book.
Yeah, I count 2 bubbles. Even my office also don't have whiteboard. So I asked them why I don't have whiteboard. They say, if you want to have whiteboard, then every other lecturer will have one whiteboard. I said, yeah, you provide everyone with whiteboard. They said, no money.
Let's say if you want to use whiteboard, you go to tutorial room. So that's why you every time you come to my office, I only got one white paper. Yeah, we even have the blackboard and the barbecue place. Newly big one. So while you barbecue, you also can write. Discuss. Discuss about ideas. You do that job free. Yeah. That's me. I just wanted to talk. Yes.
Teacher. 可以啊，可以啊，可以啊。Yeah, you can do first. Then whoever finish, you can come out and present. That's 下次那个 course structure 要加一个 presentation，一人3-8天。嗯嗯哼，有。
Saya takut menangkap pesan saya terus. Saya masih tak mau tanya. Dan ada yang dekat pasti ada. Dan ada tadi tanya berbagai Indonesia dan soalnya我知道就是因为你用这还有 K 5，也不用去看，这是都出现有 K 5是那个就不是有这个完全不是这样的。 这其他的不是吧？呀，一个颜色。呀，可能。有那个那个上钩，你有那个的，好像这个还够吧？这个有点窄。
忘了。嗯。 你们上次说那个课代表是哪一个人？代表啊，是哪一个人？课代表
一长
啊，对，在哪里？哦，女生是哪一个？哪个啊？白色衣啊，金色衣服，哪一个是姓？姓啥？
一长在
哦，就他
个人
在哪里？在哪里？在哪里？
跟这个不一样，
你讲还有一个哦
我会找到
没有在，还是这样？没有了，要么紧，要么温的，温的，W M 温温兆林哦，温兆林，
对，今天天定，红天定，do ah no man ah one question which question the first one huh? Try it try try
，Euro here come here come here here 啊，PC 啊，对对对，肯定我要讲话，我要讲很说哎，嗯，要不要用我？嗯，不能讲，因为它不是学 Discrete，不能唱，明了用这个，哎，我这个，这个，哎，嗯，这个，
看我的颜色的算法这个，这个好像这里，这个
It's not is never because
那里的颜色。 有点的满足。
It's tiny because it can be withdrawn until
Bằng đi mà. Okay. 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 And then, so next, so we got an email, we got a mail here. Johnny, for June. Which question? Yeah. So why? You say it.
For question A, there's no planar graph or like there's no kind of how many.
So why?
So I just keep redo.
Huh?
I just keep redo and we couldn't find it.
It doesn't mean don't have. How? No matter how many times he draw, cannot. So how?
Stop.
Okay. Okay. So you cannot. So you need to have a way to prove that it is non-planar. So how many? No matter how you draw, the suggesting a way to see why is it non-planar. Okay. If you try to redraw, I think you will get something like this. Okay. So I think you'll see that you can't move this line anywhere or how to move this vertex. So this should suggesting either K33 or K5 is hiding inside here. Okay. So if you try and guess, try to find K33 inside here. I already placed this different color to note that because K33 is bipartite, so I can use this bipartite characteristic to draw this K33 out. Okay, and then you make sure the line join as in how you join in K33, and then you can find a subgraph that is homeomorphic to K33. Or you can use the contrapositive. Okay, contrapositive of the corollary that we mentioned last time. Corollary for the Euler formula, right? We got 3 corollary. So one of them is to use that formula. Is you violate the what's that the necessary condition for planar graph. Okay. Show that E is greater than 2B minus 4. So it is not planar. or you can use the diagrammatic method. So what do you mean by no matter how you draw, you cannot draw? So for example, if you draw this isomorphic graph here, okay, so you should argue no matter how you place these four vertex, you cannot avoid edge crossing. But you can see that these four vertex are symmetric here. So you just need to discuss one vertex. Okay. So one vertex here got how many regions you can put? You can either put it here, or put it here, or put it here, here, and outside. Okay. So there are five regions that you need to discuss. No matter where you put this C, you can't avoid edge crossing. Okay. No matter you put it. Yeah. Repeat again. Yeah. So if you try to draw this isomorphism of graph here, okay, then you still see some edge crossing, right? Okay. So you need to discuss whether the placement of four of these vertex at different places can uh, result in no edge crossing or not. Okay. So I mean, you can swap or whatever you want to do, but my argument here is you just need to look at one vertex is enough because it is symmetric. Okay? If you, for example, if you move C down to D, it's the same as you move D up to C. Okay, so you just need to look at one vertex is enough. And then looking at one vertex, you have five regions to consider. Okay? One is outside here, which is already here. Second is inside here. Third is the innermost. And then fourth is on the left side. Then five is on the outside. Okay. C, yeah. So you can take C and then try and place it here. Then see if you can avoid edge crossing or not. Or you can place it in 3, or you can place it in 4. Okay. See if you can avoid the edge crossing or not. And place it in 5. And then you can see that no matter where you put, these are all the possibility where C can appear. Okay. This one is more problematic. If you can find a subgraph, then it's good. Or you can find a subgraph that's homeomorphic to the K3 or K5, or you use the corollary. If you can't remember the corollary, I think the most useful one is this one. But to use this, you need to be able to see K3 and K5. Okay. Okay. Let's try one more. 纪念盒，纪念盒有个 Which question you gonna do? I come try. Okay. How you gonna do? Huh? 18. 10%. Okay. Huh? Ibu laptop table.题目啊，题目我看看。bring, yeah, bring. 题来了，来。
It has K connect.
Question
18.
18.
18. So I will write K singular.
Explain lah.
I'll just keep
Huh? So why do you add all of them?
These are connected components. So
But when you add all of them, doesn't mean you repeat the region.
yes.
Huh? Right.
And there are K components, so I separate.
Yep.
K. 就把它变成了 K 个公式。
Then what if you have when k equals to 2, okay? What? Sorry. If you got these two cases, right? Okay. So first one you have region 1. First one you also, second one you have region, okay, maybe 1, 1 and 2, 1, okay? Because this one refer to this first one, this one refer to the second one. But when you add out the region here, isn't it become 2 region? But in this case, when you look at the whole thing, you only have 1 region. Right. So isn't it you already add extra thing in when you compute this R? Right. You add extra region.
In this one, it has one region.
Correct.
If I
This one has two.
Two.
Mhm. K connected component, right? So we got one connected component here, and then second connected component. But R is the region, right? So what she wrote here is this R1 is computing for this connected component, and then RK is different connected component, right? So the question asks about the whole graph, the planar graph that contains this K connected component. So for the whole graph, the R should be just one, right? But separately, they have one. So if you add all of them together, then you get extra. This is what I say. Okay. So what I say is R is not equal to R1 plus R2. So the number of regions of the planar graph is not equal to the separate sum of. Okay. So one trick you can do is you can connect them. Okay. So if you have K connected component, you can use K minus 1H to connect K of them. Okay. So that they make up a whole planar graph. Only one connected component with one connected component. Then you can use R equal, because when you add K minus 1H, you doesn't increase the region, right? Because you didn't form the boundary. So the number of region is still the same. The H will become E plus K minus 1. Okay. And then number of vertex also didn't change, because I only add H to the K connected component and then plus 2. So this is the formula. So you add K minus 1 edges to connect the changing number of region and vertexes. Okay. 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 So this one is one of the question using Euler formula. Any question on this one? So I connect all the connected component become one connected component. So I form a planar graph, then we can use the Euler formula again. Yeah. No? No, why no? You don't say, I don't know why you don't understand. But Okay. Okay. So mostly these questions are showing the planar graph. Because 10.7.11, we show diagrammatically K5 is non-planar. Similar to showing K33. And then 7.12.14 use Euler formula. Only on 12, you need to be careful. They tell you degree. Okay, so you need to transfer to H. So you need to use this handshake formula. And then you need to get H before you can compute. Then okay, one thing I want to discuss is about the chromatic number. Okay, this one from graph from map go to graph you should learn. So all the connected length you can represent by a vertex. And then when they share the boundary, you draw a edge. Okay. And then from here you figure out what's the chromatic number. Similarly, this case here, all the length you can shrink to a point. Okay. And then draw a line when they share a boundary. Okay, let's look at this one. So if you given a graph, you want to find the chromatic number, first you color your graph first. Okay. Once you produce a graph coloring, the chromatic number is less than equal to the number that you need to color your graph, because chromatic number is the least number. So the least number must be less than or equal to the number you use. Okay. And then next, how do you show that chromatic number of G is greater or equal to 3 in this case? So in this case, you should see that there's a triangle here. Okay, once you have a triangle, because 3 of them are adjacent to each other, so you need at least 3. Okay. So these two arguments you need to produce. Okay, why is it greater or equal to 3? Why is it less than or equal to 3? Okay. Similarly for this one here. So when you try to color it, you should need at least 4. Okay. So the chromatic number of the graph is less than or equal to 4. But you want to show that it is equal to 4. So you need to show that it is greater or equal to 4. So why is it greater or equal to 4? Because it contains a complete graph K4. Okay. So why complete graph K4? You need 4, at least 4, because yeah, each of them are adjacent to each other. So you need at least 4. And actually, this is the reason why you introduce this color. When you color the graph, right? So why you can't color the other colors? Exactly because of this line. So that you cannot color it. So it is really because of it contains this subgraph here. And then there are some few proof questions just for fun. Won't be in the exam. Okay. So this tutorial you have to know how to compute the chromatic number, how to show something is planar or non-planar. Either you use homeomorphic, the Kurostovsky argument, or you use the column, or you use the diagrammatic, and then see that you cannot avoid edge crossing no matter how you place the. To show something is planar, you just need to produce a planar representation. You just need to draw one isomorphic graph which has no edge crossing. Okay. How many questions? Sleep until don't want to leave already. Again. Yes. If not, you next week please be prepared for the quizzes.